Good afternoon, everyone, and thanks for taking the time to be here. My name is Ryan Shields, and I'm a master's student at Brigham Young University. So a little bit of a different topic for today, where we've been working in the Caribbean using remote sensing to assess changes to the benthic habitats there following Hurricane Maria in 2017. Dominica is a small island developing state situated at the very east end of the Caribbean plate. It's just this really unique island, and it's still volcanically active and has this rugged terrain and a very, very narrow, steep coastal shelf. With this unique geography, it also faces some unique challenges. Most recently, it was just absolutely devastated by Category 5 Hurricane Maria in the fall of 2017. Some have said that destruction just set the island back 20 years at least. And following that event, the Dominican government declared that they were pursuing this really lofty goal of becoming the world's first climate resilient island. And so we set out to help them in that quest using satellite imagery, some ISO data classification techniques, and raster color slicing to detect changes to two of the most important habitats there, seagrass beds and coral reefs. So the coral reefs, like these seen in some of our field footage from Scott's Head, this is one of their marine protected areas. These reefs absorb wave energy from incoming storms, and they just play a key role in maintaining high biodiversity, which is critical for industries like fishing and tourism. So you can see those reefs skirting the edge of the peninsula here. Seagrass, let me put the volume here so you don't have to hear that. The seagrass beds are equally as important for maintaining high levels of biodiversity, and they too help absorb wave energy and also provide carbon sequestration services. In Dominica, there are two native species of seagrass, Thalassia testudinum and Syringodium filiforme. And then there are three invasives, Halodula rhydi, Halophilus decipiens, and Halophilus stipulacea. So we were able to undertake this project because just a year earlier, the Nature Conservancy had actually developed a benthic habitat classification using Pleiad and Worldview 2 imagery, and so this acted as the baseline for our change detection, and the training data for this was generated from field surveys and video transects and GPS points, and they elected to use an object-based approach versus the traditional pixel-based method, just because it can overcome some of the limitations of visible light attenuation that can sometimes limit the mapping of submerged features. And so we use the multi-resolution segmentation algorithm and eCognition developer suite, and then the nearest neighbor classifier as well, getting that training data coming from those field surveys, and then use the merge region tool to help clean it all up, and then some heads-up digitization to get some of the reef areas that it had missed. And it really just gave incredible detail from what was available before. There was a layer of scale complexity with it, since it was done sort of at a regional level. It was classified at the same time as St. Lucia and Antigua because the training data was all taken from around the same time. So the advantages of this are that because these islands have relatively identical benthic environments in terms of things like substrate type, marine life, all that, theoretically the reefs in Dominica should appear similar to those in St. Lucia on the imagery. And by doing all three at once, you could actually use all the field data points to train the classifier, getting a little more accurate classification as opposed to just using the 100 points individually at each island. Now the disadvantage to that is that even if the images are captured on the same day, which they weren't in this case, or even on the same days as the field collection, which they also weren't, the local variations in geography and water clarity and things and atmospheric conditions can really limit or inhibit the ability to get that good bottom reflectance to delineate those features. And so in this case, even though we got the best imagery available and we maximized the training data by doing all three at once, there were some errors just because of the differences in island geography. And so here's our field team that was out doing those field surveys and collected all that excellent training data for us. This is Dr. Steve Schill from the Nature Conservancy who led the team, and he's on my committee. They went out and rigged up this boat to collect bathymetry data as well. So here you can see in this left image there's a transducer with the GPS unit on top, and then they had this tow camera that they would throw overboard, and they had a 30-meter cable to work with. They could get real-time video that would come through on this monitor or on some VR goggles, and then they would take a GPS point at the start of the transect and at the end, and then they could monitor their depth recordings and such, and then the final videos were on the GoPro. So here's a video that kind of highlights the fun working conditions doing that.
Hey, almost there. Okay, hold. On the bottom, up. Hold. Down. Yeah, not so much. Yeah, you're right there. Hey, almost there.
So they collected probably about at least 150. I know they collected at least 150 in Dominica and about that same number in Antigua and St. Lucia. We then went through and reviewed the videos and looked at the spectral signatures at those GPS points and assigned classes to them. And so these are just examples of the different classes we assigned. We were primarily interested in seagrass and coral, as I mentioned before. Specifically, this Acropora framework that's increasingly rare. So here's the maps. This is showing the training data. These are the GPS points, and then after they were put into that nearest neighbor classifier, this was the end result we got. As I mentioned, we also had the bathymetry equipment on board, and so we used that and the satellite imagery to develop this bathymetry model. And it just really did a beautiful job of highlighting just how narrow that coastline is, and and that was a big challenge for us during the project. So here's a close-up of that classification. It was just a really beautiful product that captured the variation of the island well. It really delineates the habitats on the leeward side here. You can see the seagrass snaking the coast, and then all this hard ground where things have a hard time growing because it's just taking a pounding from the Atlantic all the time, and just the variation of habitat you get over here. As I mentioned, there were some imperfections, and you can start to see those coming through right here, where you can actually see some gaps along the side of the island. And in this case, here's a close-up. It seems that this would just be a case of location error. And so if we just shifted it left, it would line up. But it doesn't actually follow the coastline exactly. So even if you slid this over, you would still have areas of rocky substrate that came inland. And this little portion to the north has kind of an arc to it. And so it would probably leave some marine space exposed that we missed. And so there was room for improvement in terms of the accuracy of the segmentation and fixing this gap. And Dominica's steep terrain really makes it a challenge to work with imagery there because it amplifies the geometric distortions in the image. And so on the left here, you have our post-hurricane scene from a Pleiad satellite, and on the right is the Worldview 2 scene from before the hurricane. And if you compare those, they look pretty symmetrical, but if you overlay them, we really start to get a sense for that terrain distortion that goes on there. And so when we were trying to figure out what was going on with that gap, we just overlaid the classification on the unorthorectified Worldview 2 imagery and actually found that it lined up perfectly. So it seems that the the geometric corrections weren't, the files that were supplied with the image when we purchased it hadn't actually been applied by the contractor who did the product. So we applied those corrections, and we went back and forth as to whether or not we would reclassify or redo the classification. Because we were on a time budget crunch, we just decided to rubber sheet the offset areas. So here you can get a sense for the difference in magnitude and direction of those. So the distortions aren't uniform across the image. So when we went to rubber sheet it, there was a transformation that you could use in ArcGIS that allowed you to draw a polygon that would isolate the transformation area there to keep the rest of it in place. Because as you can see, it's in these steeper areas that it's more distorted, but down here in the coast, that island didn't really move a whole lot, and that peninsula didn't change as much either. So sort of a silver lining to the hurricane is that it allowed us to work specifically in Dominica, and we could really hone in and fix some of these errors and adjustments, and this got us closer to our baseline that we needed to do this detection. We also came across some field data that we hadn't used in our pre-hurricane product. And so this was a 2015 survey of Dominica's reefs by Sasha Steiner. And so they went out, and these were actual in-field surveys. And so they collected coordinates and other attributes about each of the reefs, as well as provided these broad details maps and these fine scale ones as well. We had, as I mentioned, the pre-hurricane product was derived from WorldView 2 and Playod imagery. What you're looking at here is a mosaic of strictly WorldView 2 imagery. Ideally, this is what we would have liked to have used, but some of the images were limited, and that's why we swapped them out for Playod, just because of the surface quality, the quality of the water surface here just made it really hard to get good feature extraction when we were doing the segmentation. And but it was really optimal for working in a marine environment because it has the additional coastal blue and yellow band, which really helps with submerged feature detection, just because the visible light spectrum attenuates so rapidly in water. So we applied the corrections to these images as well, and we used dark object subtraction, and then to do the radiometric corrections, and then we segmented these again in eCognition Developer to try and pick out these nice clean reef features. So this was what the majority of the image looked like, and it was just spectacular to be able to work with. So we overlaid those maps from the field surveys on there, and then we took our segments, which you can see a snapshot here on the upper left, and we selected the segments that overlapped with these field maps, and that was where so we also wanted to do more beyond that. We were looking for this kind of signature yellow, brownish red color that you often get in reefs and satellite images, and we could see some of that further on up the coast beyond the extent of these survey maps, and so we wanted to include those as well. But you can see the glint on the image started coming through to be problematic, and that's where those additional bands really came in handy. So here you're looking at, we used the coastal blue, a green, and a yellow band to visualize that. We could kind of preserve the color, the natural color a little bit to look at that. And then when we really wanted to, punch down through the water, we could use the coastal blue, the blue and the green, and get that stark outline shape. So we were able to use some spectral interpretation, incorporate some field surveys, and we got this really high detailed layer. And you can see the side-by-side comparison here. On the left, you've got the original pre-hurricane product, and on the right, we've added these reef layers and cleaned up the geometric errors in a few areas. And so with that, we could now move on to our change detection. So on the left is the full extent of the seagrass beds before the hurricane from that 2016 classification. And on the right is that same area, but we've clipped it to the 10-meter contour. So here you've got 10, 20, and 30-meter bathymetric contour lines. And we did this for two reasons. One is that this 10-meter area is the range for the remaining native seagrasses that they'd been reduced to that in 2013 as this invasive seagrass of Halophilus stipulacea was spreading. And so we wanted to look at changes there to see what the consequences might be for that native species. And then that depth would also allow us to get better bottom reflectance, which was necessary to get a good result for our pixel-based classification. We had to opt for a pixel-based over an object-based because our segments just weren't coming out very well with the water quality and the Pleiad and Dovesat scenes we were using. So we used a pixel-based, and I'll explain a little bit more about that here in a minute. And so an increase in seagrass in this area might be bad news for the native species. So here's our imagery. On most of it was this Pleiad imagery from February of 2019, and these were some planet scenes that we used to fill that small coastal gap there. It's really hard to get good imagery in Dominica because the cloud cover is so persistent. So it further complicates the process as you patch in more images. So we then, as I said before, we masked that to the seagrass. So this is what it looked like after we applied that seagrass 10-meter mask. We did the same with the sand. And so this is the sand in the 10-meter areas. And what that did is that created these null hypothesis areas where if there was no change between 2016 and 2019, then these areas should be full of seagrass and sand still, respectively. So we then ran that ISO data classification. So you can see that output here. And then we looked at the several dozen classes. We just sorted through them and examined each one to see, do any of these look like they're capturing or representing seagrass or sand in an area where they shouldn't be if there hadn't been a change. And so we isolated those, we picked out those classes that looked as though they were changing. So the ones that are tinted red here are the areas of loss, and the ones in green over here and down here are the areas of gain. And then we burned that into the classification in the pre-hurricane classification to get an updated map of the post-hurricane habitats. And at a broad scale, there wasn't a significant difference, but up close, it really, you could see a significant impact, and you can see, how much loss we were getting down along this that shallow 10-meter area. So here's what we found. It turns out that Hurricane Maria didn't slow down the trajectory of seagrass expansion any. If it did slow it down, it really only brought it down to just below the trajectory level. Maybe it was exponential before or something, hard to say, but it's at least continuing on that same path that has been. Down here in 2007, this was the first time that this invasive species I've mentioned, stipulacea, was first spotted in Dominica. By 2013, it had totally edged out this Decipian species, and it accounted for the majority of the seagrass in Dominica at that point. The stipulacea did. So then this number from 2016 is from that satellite survey, and so the remaining native species actually potentially could have been gone by here. It's hard to say, but on the off chance they weren't, we wanted to look at that 10-meter coastal shelf. And so by adding our numbers into the mix, we estimate that there's about 1,260 hectares of seagrass in Dominica now. They hypothesized that between these two timeframes here, what was a big driver for that increase was the fact that 14 tropical storms passed through that area during that time frame, and 3 of those were hurricanes. And so the wave energy, even though they didn't make direct landfall, would rip out those native grasses and allow that more resilient stipulacea to creep in. And so you can only imagine what the potential consequences, what we thought the consequences might have been with something like Hurricane Maria that made direct landfall in Dominica. So here on the bottom left, here's kind of a summary. So this was how much seagrass was in the 10-meter zone in 2016. Here's what was there in 2019. This loss area right here is kind of the big thing to focus on. This, again, because there were losses in that 10-meter shelf, we need to go in and see now if that actually does mean the end of some of these native species. This expansion most certainly means that Stipulaceae is still going. We also mapped the coastline from before and after and found that there had been some accretion and some erosion that occurred. And we were really surprised to see sediment in the water column in our February 2019 image, because that's at the height of the dry season. And so we mapped that sediment and found that 400 hectares of reef intersected with it. And then you can note that there were 1.6 hectares of reef affected by accretion. And so the biggest concern were these Acroporis species, since over 43% of them fell within the accretion or sediment boundaries. Here you can see these reef layers overlaid with sediment and just see how much intersection was going on there. The sediment, to map this, we actually just looked at the image and did some sampling of different spectral values across the image to get kind of the upper and lower ends of the spectral range, because you could clearly see it in the image. And then we just did a density color slice using those upper and lower values, and then intersected that with the reefs to calculate the area. So the sediment was actually problematic for the seagrass analysis portion too. We wanted to do that object-based classification, but nearest neighbor was having issues distinguishing the sandy bottom from the sediment, and so we opted with that isodata classifier. But it also was kind of getting confused between the two types, the suspended and the sandy bottom. So we went through and we actually we took the seagrass output, the gain and the loss output, and just erased it using the sediment layer to just kind of remove that from the equation. And that's why we have that range of somewhere between 800 and 808 hectares of increase. So there was some uncertainty there, but the sediment told another interesting story with the reef. So it was, kind of a double-edged sword there. So as I said, based on our results, it seems very likely that this Stipulaceae species is still spreading, and it's even moving into shallower waters. You can see here what the native species was doing in 2013, had a really good range next to the coastline. Now it had just been, this was 2007. In 2013, it had been reduced right up to the edge. Now, this may not be all bad news, because overall, more seagrass means more CO2 sequestration and better wave energy absorption. And some studies actually suggest that these Stipulaceae meadows support larger fish and support the same quantities of fish, but they do support fewer juvenile stage fish. So we may need to look at some management solutions to protect some other habitats and areas that do support those juvenile stage fish, to make sure that those industries stay healthy and such. And so this is kind of where we're at now. We're left with needing to do an accuracy assessment, but we haven't been able to get down there and do that yet. Obviously, for travel restrictions and things, we'd like to know what the species composition of the meadows are at those expansion sites, and be able to know if those turbidity levels are higher than normal, and knowing whether our image is an anomaly. So we're waiting on some weather data to do that. So this is just a really much needed product for Dominica and its recovery. They're still, 3 years later, really at the start of the recovery process still. But it was really awesome to see the power that these Earth observation tools could have in bringing them some answers and some management solutions. So I'll end with that and open it up for questions if anyone has any.